Hello, I'm Dr. Charles Knight, and this is my 10 lectures on ecosystem ecology. I'm a professor of biology in the Biological Sciences Department at Cal Poly in San Luis Obispo. The paper I'm going to look at today, or this target paper for the class, is target paper 8, and it's on carbon dioxide exchange over multiple temporal scales in an arid shrubland ecosystem near La Paz, Baja California Sur in Mexico. It was written by Walt Oschell and Tom Bell and some other scientists in the middle, but I usually focus on the first author and the last author. And I'd just like to talk a little bit about Walt Oschell and Tom Bell. So Walter Oschell has been a professor at SDSU, San Diego State University, for 40 years. He got his undergraduate degree there in 1966, so full circle. He came back and taught there. I think he taught somewhere else for a while. I can't remember exactly where. He got his PhD in 1970, and he's had an incredible research career for his California State University. You look at his CV, and he's basically had $1 million of funding every year, basically, since he's been at SDSU. Set up a whole institute there, has been the advisor for PhD granting collaborations with, I think, UC Davis or some other UC system where students could get a PhD at SDSU. That's very unique for the CSU system. And if you look at his publications, it just goes on and on and on. There's so many papers and amazing productivity. I think I forgot to mention on the previous slide that this paper was published, I think, in 2013 in Global Ecology, or Global Change Biology. So this paper is actually, older compared to some other ones, but it illustrates, some principles from Chapter 5 of terrestrial ecosystem ecology that I think are really useful. Walt Oschell's research program's been on studying the interconnections of terrestrial, atmospheric, and marine systems. He's done studies in the Arctic, including Alaska and Russia, the Pacific Basin, including Baja California, Mexico, Indonesia, and semi-arid ecosystems of Italy and San Diego. He uses all kinds of technology, including drones, eddy covariance towers, soil measurements, of course, remote sensing and modeling. At the time, Tom Bell, the lead author on this paper, was a graduate student, I would assume, a master's student with Walt Oschell. He got his master's degree at San Diego State University in 2011. The paper was published in 2013. Probably the data, you'll see the data is from 2002 through 2008, I think it is, from this paper. So that's just the way science goes. It takes a while to get these papers out, but I'm sure that Tom Bell did a lot of his master's degree research compiling and analyzing these data from a FluxNet tower that they set up in Baja. So Tom Bell, though, had an interesting trajectory. He got a law degree in 2006 at UC Berkeley, as well as a degree. He double majored, I guess, in integrated biology and law. That's a pretty ambitious double major. Then went to SDSU, and then got a PhD at UCSB, and now he's a research scientist at Woods Hole Oceanographic Institute in is it Connecticut? I forget, or is it Massachusetts? I think maybe Massachusetts. His research focuses on understanding how the abundance and physiology of foundation species are spatially structured by environmental dynamics and biotic interactions. So that's him with a drone. I don't think that was part of this research, but new technologies, students like to see this being used, and both Walt Oschell and Tom Bell are using that kind of technology, as well as artificial intelligence and other things to analyze these big data sets. So I've got some glossary notes to begin with here. I read the abstract, and I look at the words that might be a little bit confusing, and I kind of have them in sequence. And so after I give these glossary notes, then I'll read the abstract. So I just wanted you to be aware of these words. Diel means denoting or involving a period of 24 hours. I'm just putting the kind of dictionary science definition of diel. You may not have encountered that word before, so I want you to know what it is. FluxNet, we've studied another paper that did analyses from FluxNet towers, and this is that global network of eddy covariance towers for net ecosystem exchange. At least that's what this paper is going to be presenting. They use the term drive in the abstract, and I want you to know that that's synonymous with influence or predict or cause. Something drives net ecosystem exchange, like soil moisture, as we'll see at the very end of this presentation. NEE, you know what that is, net ecosystem exchange, and that's measured by CO2. That's in contrast to NEP, net ecosystem productivity, which is measured more in biomass. Carbon sink is a negative NEE. This is going to be really important in this paper, and I've got some example test questions for you later on. And carbon source is a positive NEE. So a carbon source is somewhere that carbon dioxide is coming off of the ecosystem more than it's going in. So a positive NEE across any period would indicate that the ecosystem is a carbon source. PAR is photosynthetically active radiation. You should know that now. Enter that in the course. And ST5 is an important metric for this paper, and that's soil temperature at 5 centimeters of depth. And we'll see that ST5 is a good predictor of NEE in some cases. And I just wanted to, this paper doesn't use this word, and the abstract doesn't either, but I want to remind you of the phenomena of petrochar. Petrochar, I'm not quite sure how to pronounce it. It's not very commonly used, but you've smelled it most likely. It's the smell after a rain, after it's been dry. That early rain stimulates soil microbial activity, and we can smell it actually in the air. Usually it smells pretty good to us. This paper is going to show how infrequent summer rains can stimulate soil microbial activity, and that actually leads to a positive NEE, so more carbon dioxide being released from the ecosystem than being stored. They don't use the word, but it's something to keep in mind, like those rains on dry landscapes and the smell indicates soil microbial activity, and that could be carbon dioxide coming off and other things, volatile compounds in the soil. So my take-home points from this paper, again, I'll read the title, Carbon Dioxide Exchange over Multiple Temporal Scales in an Arid Shrub Ecosystem near La Paz, Baja California Sur, Mexico. First point is they put up a FluxNet tower in Baja California. Cool, they did that. They entered this tower into that global network of eddy covariance towers. PAR drove variations in NEE in the wet growing season. So in the wet growing season, if it was sunny, there was greater NEE, and actually I should say more negative. So it's greater magnitude, but it's negative. It's carbon being stored. Increased soil temperature led to a positive NEE in the dry season, so loss of carbon. So if soil was hot, carbon's being lost from the soil. So that's something to know, and this paper shows it well. And yeah, so hot days in a dry climate, there's more respiration happening in the soil on that stored organic material, and CO2 is coming off the soil. More precipitation led to a longer growing season and negative NEE, so kind of what you would expect. If it's been a wet season, you're going to see more green plants, more carbon being stored in the system, and that will be a negative NEE. Small precipitation events and increased precipitation frequency may increase microbial respiration and increase NEE, make it positive. This is where that word petrochar comes in. Small precipitation events, increased in frequency, so small but frequent, not enough to really soak into the soil too far or for too long. That's going to increase microbial respiration and increase NEE to become positive, more carbon coming off the system, and no carbon storage essentially. And we'll see that as we go in this paper. So I'm going to read the abstract. This is just what I do. The authors thought a lot about it, so we should just take time to read the abstract, and I'll try to do this fairly slowly here. Arid environments represent 30% of the global terrestrial surface, but are largely underrepresented in studies of ecosystem carbon flux. Less than 2% of all FluxNet eddy covariance sites exist in hot desert climate. Long-term datasets of these regions are vital for capturing the seasonal and interannual variability that occurs due to episodic precipitation events and climate change, which drive fluctuations in soil moisture and temperature patterns. The objectives of this study were to determine the meteorological variables that drive carbon flux on diel, seasonal, and annual scales, and to determine how precipitation events control annual net ecosystem exchange, or NEE. Patterns of NEE from 2002 to 2008 were investigated, providing a record with multiple replicates of seasons and conditions. Precipitation was extremely variable, from 55 to 339 millimeters during the study period, and reduced precipitation in later years, 2004 and 2008, appears to have resulted in annual moderate to large carbon sources, that's positive NEE, 62 to 258 grams of carbon per meter squared per year, in contrast to the previously reported sink from 2002 to 2003. Variations in photosynthetically active radiation were found to principally drive variations in carbon uptake during the wet growing season, while increased temperatures at 5 centimeters in depth stimulated carbon loss during the dry dormant season. Monthly NEE was primarily driven by soil moisture at 5 centimeters depth, and years with higher magnitude of precipitation events showed a longer growing season with annual net carbon uptake, that is negative NEE, whereas years with lower magnitude had drier soils and displayed short growing season with annual net carbon loss, that is positive NEE. Increased precipitation frequency was associated with increased annual NEE, which may be a function of increased microbial respiration to more small precipitation events. Annual precipitation frequency and magnitude were found to have effects on the interannual variability of NEE for up to 2 years. So there's a lot of data in that figure, and in this abstract, and we're going to look at a number of figures from the paper. But the reason I chose this paper is the figures are fairly simple to understand. I've kind of broken them down for you as I normally do, so I hope you're able to follow along. But first, I want to give you some backstory. Where is this site? In the upper right-hand corner of this map, you see the compass directions, and then you see a circle around basically the southern tip of Baja California, and La Paz is a city near the tip of, well, close to the tip. It's not Cabo, but it's closer. It's down there. It's quite a ways down Baja, near the tip. And that line kind of outlines a valley close to La Paz, and this study site was close to the edge of that outline. And I have the coordinates of the study site shown here in the El Carrizal Basin south of La Paz. This is where the FluxNet tower is. This is what it looks like in a drier time of year. That's probably the FluxNet tower in the background, and then this is during a wetter time of the year. So it's just like it is up here during the wet season. The landscape looks pretty green, but during the dry season it's much drier. So this is the first figure. It's pretty easy to understand, but I'll focus your attention on details of each of the panels individually on the next slides, because there's too much to see right here, and you can't read the axes. One of my pet peeves is small axes labels. So I'm going to show it with expanded or highlighted axes labels. So this is air temperature across the months and across the years. So we're looking at 7 years, from 2002 to 2008. Every year has a different symbol. Every month has a different value for mean air temperature Of course, in January it's at the lowest. In July and August it's at the highest, and air temperature is typically measured at 1.5 meters. So it gets up to, on average, higher than 28 degrees Celsius, and that's across the whole day, night and day. So of course during the day it's probably getting up to 40 degrees Celsius at some times during August and September, but on average it's well, lower, because the average is that every night it's colder. But you see this typical pattern of increasing from January through August and September, and then declining pretty rapidly in the fall. Nothing really unique to see here, other than just focusing on the way that this graph is oriented. That x-axis is going to be the same on the next three or next two charts. Also dealing with all 7 years. This is net radiation. Also, well, there's one thing I want to point out. Also across the year, there's variation, more net radiation, or PAR. They don't put PAR here because they're measuring it in watts per meter squared, but that's the different measure of photosynthetically active radiation. We're looking across all 7 years, and what I see is most interesting is that in September and October, and maybe even July, there's quite a bit of variation in net radiation. So those would be due to summer storms that come through, and there's more clouds, and so there'd be less. For example, in 2002, in July, there was a lot less net radiation than there were in other years, and also there's variation, quite a bit of variation in September. Similarly, in September of 2004, it looks like there was a lot of storms that came through, decreased net radiation. I expect there was greater precipitation in those years. Just want to point out the variation. In general, from January through May, they're all pretty similar year to year. Last figure in this panel of figure 1 is volumetric soil moisture at 5 centimeters of depth. So they dug a pit and they measured volumetric soil water every year, every month, and they have this data, a lot of data, but it all converges. There's a lot of variation, January, February, March, and then it just converges. May, June, July, pretty much it's going to be dry. It's just dry at 5 centimeters of depth. That's just the way it is in this system. When the wet season starts depends. It definitely starts in September almost every year. Certainly in 2002, there was a lot of precipitation compared to other months, but other years, that is. A lot of variation in soil volumetric water content at 5 centimeters from September through March, I'd say, in the winter months, but really very much converges during the summer months to very low volumetric soil water content. I want to focus on this month of this year. This is January of 2002. We're going to look at that month of this year first, of 2002, and then we'll look at July of 2005, which I should have highlighted, but you might be able to find it. It's the open triangle of July. So this panel in figure 3, it's pretty easy to understand, but it shows 2 different months, and the axes are way too small to see, so I'm going to look at figure A first. These are average hourly observations in January of 2002 on figure A, and July of 2005 in figure B. So important to know, there's quite a bit of difference there, but I'm going to look at each one individually. We'll start with A. This is A, January of 2002. So you got 2 different variables being plotted here. NEE is the solid line and PAR is the dashed line. The axes labels are too small, so I put them on bigger. I just go to the PDF, expand it when it's large, do a screen grab, and then paste in the larger label, larger axes labels. Like, my biggest pet peeve on student presentations is you just can't see or read the axes labels. So we got 3 axes here: NEE, PAR, So those are the two y-axes, and then time of day. Important to know that these are average values across the whole month. So 6 a.m., you got 30 observations of NEE at 6 a.m. and 30 observations of PAR at 6 a.m. Clearly there's 0 PAR. The sun hasn't come up yet. And NEE is positive. CO2 is coming off of the soil. But then later in the day, from it looks like 8 a.m. on, NEE becomes negative. The landscape is storing carbon. Important pattern. NEE goes from being positive at night to negative during the day, and then positive at night again, and it pretty much tracks PAR. So a good question to ask is, did this ecosystem store carbon in January of 2002 across all days? You have to do your integration of area under the curve. I'll give you some chance to think about it, and we'll talk about it in class, but I want to do this in class and have you figure this out. You could use scissors, that might be helpful, and maybe I'll bring some to class. Here's July of 2005. Very different story. NEE is almost always positive across, these are again 30 averages of every hour of the day, but in general NEE is positive, just barely dips to negative around 7 a.m. When maybe there's some morning morning dew or something that drives a little bit of photosynthetic activity that stores carbon. PAR is also this is soil temperature at 5 degrees or 5 centimeters of depth. And I gotta go back. This is soil temperature at 5 centimeters of depth, and not PAR. The dashed line, the previous graph was PAR, I believe. This one is soil temperature at 5 centimeters of depth, and you can see the correlation between elevated soil temperatures driving increased NEE, that is positive NEE, during the summer months. And I think that's the point of this graph. PAR is driving negative NEE during the wet months. Soil temperature is driving positive NEE during the dry months. So again, did this ecosystem store carbon in July of 2005? I'll let you consider that. We'll talk about it in class. Here is all of the months of all of the years, same data as that previous figure. This is figure 2 actually, but really so much data to see here, and it just has tons of good test questions. When students ask me, did I cover anything important in class today, I say, well, I was just giving away test questions the whole time. So here's 2. Did the ecosystem store carbon in X month of X year? So let's say in February of, let's say 2006, or actually I want to look at, I don't see very well, but yeah, let's say February of 2004. That looks like an interesting month. What about February of 2002? Those are the types of questions I could ask on the ask on the test with this graph. You might need to have some scissors or some way to actually integrate that, but those are reasonable questions. Or I could ask what month and what year showed the most carbon storage, and I'll let you again think about that. We will talk about this in class. So the last figure I want to present today for this paper is a predictive relationship between soil volumetric moisture content. Remember, they collected that every month of every year that they did this study. That's actual boots on the ground, I think. I'm not sure if they can do that automatedly. That'd be a good question. Maybe they have TDR sensors in the ground that can measure it remotely. Maybe they do, because that'd be a lot of work every month to go in there and measure volumetric soil moisture. But regardless of how they collected it, they have it for every month across many years. And they plot volumetric soil moisture versus NEE, And remember, when the value is positive, that's a carbon loss from the system. When it's negative, that's carbon storage. So the wetter the soils, the more possibility of carbon storage in the system. The drier the soils, the more it's likely to be a net source of carbon from carbon dioxide from the soils. There's a dormant season in black dots, the growing season in unfilled dots, and I don't think that matters too much because it's really just the volumetric soil moisture versus NEE. All right, I'll go back to my take-home points. First, they put up a FluxNet tower in Baja California. That's really cool. Second, PAR drove variations in NEE in the wet growing season. Second, increased soil temperature led to positive NEE in the dry season. More precipitation led to a longer growing season and negative NEE. And then small precipitation events and increased precipitation frequency may increase microbial respiration and increase NEE and actually make it positive, so CO2 is coming off the system. Okay, thank you very much.